Hello everyone, it's my honor to join the 35th ACM Symposium on Applied Computing. Today I want to talk about our work, a novel network traffic classification approach where discriminative feature learning. Traffic classification is aimed at automatically associating network traffic with the generating application. It can provide valuable information for quite a few network operations, such as quality of service, network monitoring, bandwidth optimization, and network security, and so on. The existing traffic classification methods can be summarized into four categories: port-based method, payload-based method, statistical-based method, and deep learning-based method. In the early days, the Internet assigned number authority assigned well-known ports to different protocols. The port-based method inspects the port number value in packet header and associates it with the corresponding protocol. This kind of method is simple and fast, but the pervasiveness of network address translation, port obfuscation, and random port assignments have significantly degraded its performance. Payload inspection techniques, most of which also known as deep packet inspection, perform traffic classification by analyzing the contents in the application layer payload of packets. They search for distinctive hints in the payload and use them as signatures for each protocol. Because the need to check the contents of payload, they are less effective when payload encryption is adopted. Beyond that, user privacy issues are also among the most important drawbacks of this approach. The statistical-based method uses machine learning techniques combined with handcrafted flow statistical features for network traffic classification. Uh, it is encryption independent, but the feature design depends on expert knowledge, and the handcrafted features are not discriminative in traffic classification for different specific applications. In recent years, researchers have begun to use deep learning techniques to automatically perform feature learning for traffic classification, and the classification accuracy have improved greatly. But the problem of within-class diversity and between-class similarity are still two big challenges for application-level traffic classification. For example, an application may use multiple protocols to achieve different functions such as login, file transfer, update, and so on. Meanwhile, different applications with similar functionality often uh, generate flows with similar patterns. Existing studies cannot obtain features discriminative enough for fine-grained traffic classification at a specific application level. So we highlight the main contributions of our work. We combine machine learning techniques with deep learning models to learn more discriminative features for network traffic classification. We provide evaluation and comparison with state-of-the-art methods on three datasets. The results show that our method provides better classification performance on all the three datasets. Here is the overall architecture of our proposed method. It contains two core modules, preprocessing and model learning. The preprocessing module converts raw network flows of varying lengths into fixed-size inputs. The model learning module learns the CNN model by optimizing a new objective functions, which adds a machine learning regularization term to the traditional cross-entropy loss. Considering that Only fixed size input is accepted by CNN, while the flow lengths are often varied. So we transform raw network flows or varying lengths to satisfy the input structure of CNN. Specifically, we keep the first 32 packets of each flow, and for each packet, we keep the first 500 and uh, the first 512 bytes starting from transport layer header. After this transformation, each flow is represented as a matrix with size 32 times 512. To obtain a better performance, we normalize the matrix and resize them to 128 times 128. The model learning module takes the flow matrix from the preprocessing module as input to turn the CNN. And in order to learn more discriminative features, we propose to optimize a new objective function. It contains two terms, a traditional cost entropy loss and a new metric learning regularization term. Metric learning focuses on finding an appropriate similarity measurement that can preserve the desired distance structure between the pairs of input data. Here we use a contrastive embedding term to enforce the extracted features to be more discriminative so that they have compact within class variations and separable between class differences. Different from the conventional learning systems where the loss function is the sum over samples, contrastive embedding is turned on paired samples. So it will produce a large sample pair space if there are a large number of tunneling samples. To limit computational cost and make the tunneling process more efficient, we consider new tunneling pair generation strategies. Uh, for each for each input pair, we replace the contrastive symbol with its class center in the original feature space. The intuition is we hope that in the learned feature space, samples are closer to their respective class centers and farther from the class centers of other classes. By applying this, the sample pair space drops greatly. We have evaluated our method and compared with the closest deep learning-based related work on 3 traffic datasets. We have collected traffic data from the machines of a working group with 20 people in an organization using a process-oriented monitoring tool. The traffic generated by different applications are automatically kept in separated pickup files from which we selected 10 kinds of applications with rich network behaviors. We use the malware traffic data maintained by the malware capture facility project as a second dataset to evaluate our method. The captured traffic of various malware is kept in separated pickup files from which we randomly selected 10 kinds of malware. And the third dataset is a synthetic dataset. It is a combination of the above two datasets and contains both normal and malicious traffic and contains 20 classes. For the OD dataset, we randomly separated it into 70% for tunneling, 10% for validation, and 20% for testing. The validation set is used to determine the best value of the weight lambda of the metric learning regularization term in our objective function. For the rest two datasets, we both randomly separated them into 8% for tunneling and 20% for testing. All the splits are accomplished using the built-in library of sklearn to preserve the distribution. To determine the best metric learning regularization parameter lambda, we vary its value and validate it on the OD dataset. We can see that the lambda has little effect on the accuracy when it is in the range of 0.05 to 1. For CNN model tuning, the learning rate is set to 0.001 for all the layers, and the L2 weight decay parameter is set to 0.005 for preventing overfitting. The CNN used for evaluation in our work comprise two convolutional layers, two max pooling layers, and three fully connection layers. This paper focuses on improving network traffic classification performance by enriching the power of the CNN feature representations. So we first gave an intuitive comparison between the distributions of deeply learned features under the supervision of different objective functions. From figure A and B, we can observe that only under the supervision of cross-entropy loss, the deeply learned features are separable, but they are not discriminative enough, since they still show significant within-class variations. Therefore, it is not suitable to directly use these features for traffic classification. The results in figure C and D show that after imposing the metric linear regularization term on the cross-entropy loss, the deeply learned features are more discriminative as they have small within variations and large between class separations. These discriminative features are more suitable for traffic classification. Next, we evaluate the classification performance of our proposed method against three datasets. We compare the classification results with a deep learning-based traffic classification method, namely deep packet of related work. Besides, we also compare the results obtained by setting the metric linear regularization parameter lambda to 0, which means that only cross-entropy loss is applied, and thus our method is degraded to the traditional CNN-based classification. By comparing the results of lambda equals 0.5 and lambda equals 0, we can see that our proposed method greatly outperform the traditional CNN-based classification. This is because that the embedded metric linear regularization term can enforce the network to learn more discriminative features, which facilitates a more accurate classification. The classification performance of deep packet is comparable to the traditional CNN-based classification, and it is also much lower than our method. Furthermore, we also report the results measured in terms of confusion metrics for more detailed comparison. All the results shown above prove the effectiveness of our method. Lastly, we summarize our work and look forward to some future work. In our work, we explore the possibility of integrating metric learning into deep learning models to deal with the problems of within-class diversity and between-class similarity when performing application-level traffic classification. And extensive experiments have been conducted on three traffic datasets to evaluate the effectiveness of our approach. Considering that most of existing studies perform traffic classification based on the assumption of closed world, where all the classes are known and fixed. Thus, they lack robustness and don't have the ability to recognize network traffic originating from novel classes, such as traffic from novel applications. In the future work, we plan to consider the problem of traffic classification in an open world setting, where traffic from previously unknown classes may exist in the testing phase. That's all. Thank you.